So in this video I wanted to talk about differentiation. How do we differentiate different functions? So let's start straight away. I suppose the most kind of basic rule is that if a function is a composite function consisting of a sum of numerous functions, then the derivative of that function is just the derivative of each of the functions that go into that. So what does that mean? For instance, if I say that f of x equals to 5x squared plus 3x and then minus natural log of x. To find the derivative of this expression, all I need to do is just take a derivative of each of them separately. So d dx, I'm just going to write that down, of f of x is equal to derivative of 5x squared is 10x. And again, that kind of arises from the ways in which the polynomials are differentiated, and we have a formula and a heuristic for it. Derivative of 3x is just 3, and finally the derivative of natural log of x is 1 over x, so minus 1 over x and 1 over x. So that's my derivative. Again, if I have a derivative which is, consists of sum of different functions, then to get derivative of this expression, all I need to do is find derivatives of each and every single element of this sum. Nice and easy. But it gets more complicated when you get into things like a product rule. So product rule tells me that if I have a derivative of an expression where I multiply two functions, then the derivative of that expression is the first function multiplied by the derivative of the second one plus the second function multiplied by the derivative of the first one. So let's see if we can take a look at an example of this this thing at work. So let's say that f of x equals to 3x squared sine x. Actually, you might note at some stage that a lot of your work comes down to recognize which of the rules of differentiation we need to use. And in this case, we need to use quotient rule, product rule rather, sorry, because we're multiplying 3x squared by sine x. So let's get right to it. Derivative. So to get the derivative of this expression, I'm noting that v of x is equal to 3x squared, and that d, or maybe I'll just do it differently, v prime is equal to 6x. Putting that dash beside the function also tells me that it's a derivative. Then my u of x is equal to sine of x. So finally the derivative of u is equal to cos x. So now if I want to find what is the derivative of f of x, is the first function multiplied by the derivative of the second one. So the first function is 3x squared multiplied by the derivative of the second one, so that's cos x. And then we add the derivative of the first one and multiply it by the second one, so that's 6x sine x. And then we could maybe take out the common factor, so for instance take 3x out, 3x, and that will give us x cos x plus 2 sine of x, and that's my derivative. Important to recognize when I'm multiplying an expression, and the expression, and this is something that we'll have to learn how to recognize when I'm multiplying functions to form an expression. So that's something that's not immediately clear, but it will become clearer as you continue working through that, through those examples. Derivative of this 3x squared times sine x, this is a product of two functions. The first function is 3x squared, the second function is sine of x. So the derivative of those two is given here. Alternative is when rather than multiplying two functions, we're dividing them. So if you have a function that consists of a ratio of two different ones, then the derivative of that function is, this is something to remember, or maybe use a handout of sorts. So that's the denominator of the expression, of the fraction rather, multiplied by the derivative of the numerator minus numerator times the derivative of the denominator, and all that over by denominator squared. So let's take a look at an example. Let's say that my f of x is equal to 4 sine x divided by 5x to the power of 4. So obviously this is a fraction, so I need to use quotient rule. Let's say that my u equals to 4 sine of x, and then u prime will be equal to 4 sin x. Derivative of 4 sin x is 4 cos of x. And then in the denominator, v equals to 5x to the power of 4. V prime equals to, or the derivative of v equals to 20x cubed. So let's put those numbers into my expression and see what comes out. So I multiplied the denominator by derivative of numerator, so that gives me 5x to the power of 4 multiplied by the derivative of the numerator, which is times 4 cos of x, and then minus numerator by the derivative of the denominator, so that's 4 sine x by 20x cubed, and all that divided by denominator squared, which is 25x to the power of 8. So if I simplify that a little bit, I'm going to end up with 20x to the power of 4 by cos of x minus 80 x to the power of x cubed, I guess, sine x, and all that divided by 25x to the power of 8. And in a similar fashion, you deal with other examples of other examples of quotient rule. Maybe we'll do one more. So let's erase that. Let's say we have 5x divided by 3x squared plus 4. So obviously my u is equal to 5x, u prime is equal to 5, v is equal to 3x squared plus 4, v prime, derivative of v equals to 6x. So then to get the derivative of the whole expression, I use the quotient rule, so 3x squared plus 4, and all that multiplied by 5, and minus 5x by 6x, and below the line I'm using, I have 3x squared plus 4, x squared plus 4, all that squared. Simplify a little bit, 15x squared plus 20 minus 30x squared divided by the same expression, 3x squared plus 4, all that squared. And then you could simplify it by cancelling the 15s, but it's the same thing. So last but not least, we have the chain rule, and the chain rule is probably the most powerful way of dealing with functions. It really simplifies finding derivatives of complicated and complex looking functions. So what does the chain rule apply to? So if a function consists of a function of a function, then the derivative of that original one, derivative of f of x, will be I guess the derivative of the outer one by the derivative of the inner one. That's how I think about this. Like, I think about those functions as boxes in the boxes in the boxes, and then to find the derivative of the expression, I just need to take the derivative of each box separately. Okay, but what does it mean? It doesn't really seem very obvious. What is a function of a function? So let's take a look at expression f of x equals to 3 cos of 5x, and compare this with expression of 3 cos of x. What I want you to recognize here is that, let me maybe change paint color for a second. There is a very important difference between 5x and x, because when you take x as an argument of this function here, the x won't change. There's nothing happening, so you can find the value of the cos immediately. But if you put the x as an argument to this expression, before you can find the value of the cosine, you need to find the value of 5x. And that's why this expression, 3 cos 5x, is a function of a function, where the inner function is 5x and the outer function is 3 cos of that inner function. So what does it mean for my finding my derivative? So I have a value, I have f of x equal to 3 cos of 5x. So what I can say is that u, the outer function, equals to 3 cos of v. I'm making a substitution. For inner function is replaced with a letter, and I can say that v is equal to 5x. So that's all well and good. I can find du dv. Note that v, the inner function, becomes the argument for the outer function. So the derivative of this is simply minus 3 sine v, doesn't change. And then dv dx, derivative of this expression, this function, is equal to 5. So using the chain rule, f prime equals to du dv multiplied by dv by dx, the derivative of the outer one multiplied by the derivative of the inner one. So that's, let's put the values in, minus 3 sine v, minus 3 sine v, and then multiplied by du, sine u rather here, dv dx is 5 times 5, so that's minus 15 sine of v. But there is something that I can change here, because I know that v is equal to 5x, so I can replace v in this expression with 5x, and that will give me the final expression equal to minus 15 sine of 5x. And this is a derivative of this function of a function. So hopefully that kind of makes sense for you. So let's take a look at another example. Let me just maybe erase this all. Okay. So let's take a look at another function. Let's say that my function is equal to say 3 ln of 5x squared plus 2. Okay, so that's, you know, probably a little bit more complicated than we want it to be, but we can still deal with it, because I recognize immediately that this is a function of a function, where outer function, we have u equals to 3 ln of v, and the inner function v equals to 3, not 3, equals to 5x squared plus 2. So derivative of the outer function, du dv equals to 3 over v, and dv dx is equal to 10x. So now I can finally find the value of the derivative of the whole expression. Dx f of x equals to du dv times dv dx, and that equals to du dv is 3 over v, dv dx is 10x, so that gives me 10x, maybe actually I write 30 immediately, 30x divided by 4v, I'm putting in 5x squared plus 2, and that's the derivative. Sometimes those chains become much longer. You might have 3 or 4 different derivatives of the inner and outer functions, but that's still possible to do. So we covered derivative of composite functions, derivatives of products and quotients, and finally we covered the chain rule, which makes it possible for us to find derivatives of pretty much majority of expressions. We might try to look at logarithmic logarithmic derivatives later on, but for now we'll deal with those. So thank you for watching, and that's it for now.